My dear students, let me welcome you all to a new edition of physics. In this edition, we'll revise Unit 1. We'll deal with miscellaneous questions. The questions will be of gradual difficulty. Also, we'll try to solve some problems. So let's get started. First question. Okay, we revise Unit 1. What about the first question? What happens when? In front of you, we've got, yes, an experiment. You know the experiment quite well. It is an experiment to demonstrate self-induction. The circuit is closed, and we want you to mention what would happen, yes, if the switch is opened. Okay, thank you very much. And we want you to account for your answer, to justify your answer. The lamp momentarily flashes. Why? Due to the high forward EMF induced by self-induction. As I said, it is an experiment to demonstrate self-induction. So the lamp flashes the moment the key is opened. What happens when? The two metallic rings in an AC dynamo are replaced with a split cylinder commutator. Two metallic rings are replaced by a commutator. Okay, the AC current becomes unidirection varying current. Okay, so the current will flow in just one direction, but it still changes from 0 to maximum and vice versa. Okay, what happens when the value of R1 in the circuit is decreased with respect to the readings on the voltmeters? In front of you, we've got two voltmeters. The first, and it is denoted by V1. Yes, what about it? It measures terminal voltage. And what about V2? This voltmeter measures the voltage across R2, but V1 measures, yes, terminal voltage. And now value of R1 is decreased. What would happen? V1 decreases, but V2 increases. Let me explain this. When R1 is decreased, yes, what happens to the total resistance of the circuit? One item of the circuit, resistance of one item is decreased. So total resistance is decreased. And this increases the current through the battery. So the lost voltage, the internal voltage, increases. So the terminal voltage or the external voltage, yes, decreases. Okay, once again, when R1 is decreased, total resistance decreases, current increases, internal voltage increases, V1, which is the external, decreases. And now, what about V2? How to determine the value of the voltage across R2? It is the product of R2 and the current. R2 is constant. So what determines the value of V2 is the current intensity. What happened to the intensity of the current? It increased, so V2 increases. So once again, decreasing the value of the variable resistance decreases the total resistance of the circuit. So the current passing through the battery increases. And this causes the internal voltage to increase so terminal voltage decreases. V2 increases as it is proportional to the current. It depends on the current, and the current, yes, was increased. When does each of the following quantities equal 0? Okay, we want you to mention in what position, okay, each of the following quantities will be equal to 0. The torque acting on a coil carrying an electric current and placed in a uniform magnetic field. We want you to mention when the torque is equal to 0. Is it in the vertical position or in the horizontal position? Okay, the torque equals 0 in the vertical position, where the plane of the coil is perpendicular to the magnetic field. So once again, torque equals 0 in the vertical position. Describing the vertical position, it is the position where the plane of the coil is perpendicular to the field. Okay, since the torque is given from the expression T, the torque equals BI-N cosine theta. Theta is the angle between plane and, yes, and magnetic flux lines. So the torque is 0 when theta is equal to 90. Cosine 90 equals 0. When does the EMF induced in a wire moving in a uniform magnetic field is equal to 0? Okay, when the wire is moved parallel to the field. When the wire is moved parallel to the field. EMF instantaneous in the wire is given from the relation B, magnetic flux density, L, length of the wire, V, its velocity, sine the angle between its direction of motion and magnetic field. So EMF instantaneous will be equal to 0 when theta is 0, sine 0 is 0. Okay, and let me remind you something. Theta is the angle between the field and direction of motion of the wire. When does the force of a magnetic field on a current carrying wire, yes, equal 0? When the wire is placed parallel to the field. When the wire is placed parallel to the field. Force is given from the expression BIL sine theta. Force equals 0 when theta is, yes, of course, 0. So the force will be 0. Let me remind you something. B is the magnetic flux density, which produces the force on the wire. I current through the wire, L length of the wire, theta is the angle between the field and the wire. So when the angle is 0, when the wire is placed parallel, the force will be equal to 0. When does the instantaneous EMF induced in a coil rotating in a magnetic field equal 0? Instantaneous EMF induced equals 0 in the vertical position, where the plane, describing the vertical position, where the plane of the coil is perpendicular to the magnetic field. EMF instantaneous is given from the expression EMF maximum cosine alpha. So EMF instantaneous equals 0 when alpha is 90. Okay. When does an AC current means is connected to the primary coil of a transformer and no current flows through it? Okay, this happens when the secondary coil is unloaded. It happens when the secondary coil is unloaded. That is to say, the secondary circuit or the circuit of the secondary coil is open. Then the current through the primary almost equal to 0, though it is connected to the mains. And now we've got another type of questions. A rectangular wire loop is being pulled to the right. Okay, your attention, we've got a rectangular wire loop placed, yes, close to a current carrying straight wire. And now the wire is being pulled to a given direction, is pulled to the right, away from the current carrying straight wire. Okay, will the current induced in the loop flow in the clockwise or anti-clockwise direction? Of course, it is in the clockwise direction. And now we've got another type of questions. What about A and B? The figure shows two vertical wires, A and B, viewed from above. Okay. The wires are equidistant from point P. So the distance from P to wire B and P from wire A is the same. Ignoring the effect of the Earth's magnetic field, draw a separate diagram to show the direction in which a small compass needle placed at P will set when a current flows upwards out of the paper through wire A and no current in B. When a current flows upwards out of the paper through wire B and no current in A. When each wire carries a current of the same value upwards. Okay, this is the first case. Current flows outwards. Okay. And what about the second case? Yes. And what about if concerning the two wires carry the same current? Okay, this will be shown in front of you right now. This was about an important question. And now we've got two circuits. Circuit A that contains a solenoid, a coil, and switch and battery. Circuit B which contains a coil, which is a solenoid, battery, and a lamp, a bulb. And what about the question? Yes, it asks about what happens to the brightness of the bulb. In the instant the coil A is pulled away, is moved away from coil B. We want to know, yes, what would happen to the brightness? Will it increase, decrease, or remains unchanged? Okay, so moving coil A away from circuit B will induce a current in B. If the direction of the induced current, yes, is in the same as the original current flowing in the bulb, the intensity increases. Opposite, intensity decreases. Okay, so, okay, thank you very much. Brightness of the lamp increases at the forward EMF induced in coil B by mutual induction. Okay? When coil A is being pulled away, is in the same direction of the battery current flowing in the lamp. So brightness increases. And now we've got a problem. Two long parallel. And now we've got a problem. We've got two long wires placed mutually perpendicular. One wire, which is X, carries a current of 2 amperes. The other wire, which is Y, carries a current of 1 ampere. And we want to calculate the total magnetic flux at point Q, which is 20 centimeter away from the 2 ampere wire and 10 centimeter away from the other wire. Okay, so once again, calculate the total magnetic flux at point Q. Okay, we'll do it one by one. So magnetic flux due to wire X, the point is located at 20 centimeter from wire X. Wire X carries a current of 2 amperes. It is equal to 2 times 10 to the power of negative 7. Current flowing through wire X is 2 amperes. Distance is 20 centimeter. 20 should be converted into meter, so 20 times 10 power negative 2. It is 2 times 10 power negative 6 Tesla. Okay, so we managed to calculate the magnetic flux density due to the wire carrying a current of 2 amperes. And magnetic flux density due to wire Y. Wire Y carries a current of 1 ampere, and it is at a distance 10 centimeter from the mentioned point, point Q. So it is equal to 2 times 10 power negative 7, current through the wire, 1 ampere, distance 10 centimeter, 10 times 10 power negative 2. Also it is equal to the same value, 2 times 10 power negative 6 Tesla. And when calculating total magnetic flux by using Ampere's right hand, okay, we'll find that the two fields will be in opposite direction. So total magnetic flux will be obtained by the difference. Since they are equal, so total is equal to 0. And now we've got another type of questions. Okay, we've got in front of you, you've got a diagram, and the question says a student disconnects the voltmeter shown in the figure, shown in the circuit, and connects in its place a battery and a switch. So a battery is placed and a switch. Your attention, we've got 2 slip rings here. Okay. But when he closes the switch, the coil does not rotate as it should in a DC motor. There is something wrong. We want you to recognize this. Okay? When he closes the switch, when he allows the current to flow, the coil does not rotate properly. Why? Okay, what is the reason for this? And what other changes will he have to make before the motor works properly? Actually, the coil will not rotate in one direction because of the presence of the 2 rings. Because of the presence of the 2 rings, the coil reverses the direction of rotation twice a cycle. Okay, what a change we should make? The 2 rings should be replaced by, yes, a split ring commutator. The split ring commutator reverses the direction of the current in the coil each half cycle to make it rotate in one direction. And now we've got a problem. A circular coil of 20 turns. A circular coil of 20 turns. Each of radius 4 centimeters. So area can be calculated. We've got the radius, a number of turns, and of resistance 2 ohm is placed at the center of a larger circular coil of radius 50 centimeters. And 10 turns that carries a current of 8 ampere in the clockwise direction. If the two coils have the same plane and the current in the larger coil falls to 0 in 1 microsecond, calculate the value of the current induced in the smaller coil and its direction. Okay. Magnetic flux in the larger coil, it is 4 pi times 10 power negative 7 permeability Ni over 2R. Number of turns 10, current 8, and radius 50 centimeter, 50 times 10 power negative 2. Okay, so the magnetic flux density along the axis of the larger coil, okay, or at the center of the larger coil, is 10 power negative 4 Tesla. EMF induced in the smaller coil is given from Faraday's law. Negative n, the negative sign indicates Lenz's rule, n number of turns on the smaller coil, delta phi over delta t, rate of change of the magnetic flux coming from the larger coil. EMF induced equal to NAB over delta t. So negative sign 20, area can be calculated pi r squared, so pi 4 times 10 power negative 2 all squared times 10 power negative 4 over time 1 micro, so 1 times 10 power negative 6. It is 10.057 volt. And now we can calculate the current. It is obtained from the relation current is equal to the voltage or EMF over the resistance. It is 10.057 over 2. It is 5.028, and it will flow in the clockwise direction. A rectangular coil 40 centimeter long, 30 centimeter wide is rotated about an axis parallel to the length of the coil in a field of flux density 4 millitesla with the linear velocity 50 meter per second. The coil has 100 turns. Calculate the maximum induced EMF in the coil, the instantaneous EMF induced in the coil when its plane makes an angle 60 with the field. First of all, we need to calculate angular velocity. In the problem, linear velocity is given. Okay? So first of all, we need to obtain angular velocity. But there is something important. Radius is equal to, yes, width over 2. So it is 32 times 10 power negative 2 over 2. It is 0.16 meter. And relation between angular and linear, angular equals linear over the radius, so angular equals 50 over 0.16. It is 312.5 rad per second. And now we can calculate the maximum EMF. It is NA B omega. Number of turns is equal to 100, area 40, magnetic flux density 32, okay. So number of turns once again is equal to 100, area length times width 40 times 32 times 10 power negative 4 times 4 times 10 power negative 3 for millitesla times the angular velocity 312.5, it is 16 volt. EMF in instantaneous equals EMF maximum cosine 60. Okay, so it will be 16 times cosine 60 is equal to half. It is 8 voltage. Okay, now we've got a solenoid and a current carrying straight wire is placed inside the solenoid along its axis. Okay. And there is a question here. The straight current carrying wire shown in the previous figure, okay, experiences no force. Why? experiences no magnetic force, although it is placed inside a current-carrying solenoid, simply because the field of the solenoid is parallel to the wire, so it doesn't exert any magnetic force on it. The force is given from the expression BIL sine theta. So the force equals 0 when theta is 0. Okay. The power of a direct current motor increases when a set of coils having equal angles among each other, together with a commutator with a number of segments twice the number of coils, is used instead of the single coil. Give reason. We want you to explain this. Okay, why the power increases when we use a set of coils? Okay, and a commutator divided into a number of segments, twice the number of coils. Okay, in this way, there will always be a coil in the horizontal position, where the torque is a maximum. So its power increases. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.